Okay, so we're now going to talk about the preparation of ethers using oxymercuration. And the first thing I need to do is refresh your memory on using alkenes and oxymercuration. So we had an alkene, and I chose this generic example because I have two different degrees of carbon. So I have a primary carbon and a secondary carbon in this generic example, assuming that R is just another chunk of carbon. And so when we react this with the mercury acetate, the mercury is the thing that acts as the electrophile. And so it goes on first to the less substituted carbon. And then it helps to stabilize the carbocation that formed on the more substituted carbon. And then water is the solvent, is surrounding this carbocation, and so it's going to approach from the other side away from the mercury. And then when it puts that third bond on the oxygen, you get a plus charge, and when it loses a proton, you get this species here at the end of reaction number 1 that has the OH on the more substituted carbon, and the mercury acetate stuff is on the other carbon, the less substituted carbon. And so at the end of reaction number 1, that's where you are. And then you treat this stuff right here with the sodium borohydride, and the hydrogen replaces the mercury, and that's how you finally get to here. Now in the process right here, when we did this reaction, we spit out as another side product an acetate anion, which I've written down here. And this is a resonance stabilized anion. And we know a little bit about acetic acid. Acetic acid has a pK of about 5, so it's considered a weak acid, but it's resonance stabilized. But because it's a weak acid, it's fairly likely that it would rather make another bond than stay like that. Even though it's resonance stabilized, if you compare it to, say, mineral acids, it's a reasonably good nucleophile compared to a typical mineral acid like HCl. Chloride wouldn't be quite as good as that at wanting to make a bond. And so when we look at this, there's a couple things we could change. If we change the solvent from water to an alcohol, then that would give us a different species to come in right here, and then when we lost a proton, we could have an ether as a product. Why would we do that? Well, for one thing, alkenes aren't all that soluble in water, so it would be a natural thing to try dissolving the alkene into other solvents, and an alcohol is able to dissolve the mercury acetate, so that's kind of a natural thing to try. And so it gives us that option of making an ether. The other thing that we need to do is deal with the fact that this guy is a reasonably good nucleophile and could compete with an alcohol and make a bond here. Now you might reasonably ask the question, well, does it compete with the water? And as the concentration of these guys builds up, yeah, it could. And we just really don't talk about it very much in this book. But what we want is to make sure that this acetate is not going to interfere with our ability to make ethers. So we're going to make two changes to this reaction to help us make ethers. So one of the things we're going to do is we're going to use an alcohol as a solvent, and that's going to be better for the alkene, and it's also going to be the nucleophile. And that's how we're going to get to an ether. The other thing we're going to do is we're going to get rid of the acetate anions, and we're going to change it to trifluoroacetate. Trifluoroacetic acid is about has a pK of about 0.5 as opposed to about 5, so it's a couple orders of magnitude more acidic, and that means the anion is less interested in being a nucleophile. So it's more like chloride ion. It's not impossible, it's just not that interested in being a nucleophile, and it's still resonance stabilized. So here's what it's going to look like. We're going to take the trifluoromercury acetate and a solvent like methanol, which will also act as a reactant. And we're going to put the mercury on the less substituted carbon, and then the alcohol will go to the more substituted carbocation, which then is going to then lose a proton. And so at the end of the first reaction, you have that mercury on there, and you still have to get it off with the sodium borohydride. And so it gets onto here. So you're still doing Markovnikov addition. Essentially, you're adding the elements of the methanol across this double bond, and the hydrogen goes to the less substituted carbon, and the O and whatever your chunk of carbon is goes to the more substituted carbon. So it's still Markovnikov addition. And here it is written in a condensed way. So I have the trifluoro mercuric acetate, and in this case ethanol is both the solvent and the reactant, and then the sodium borohydride. And in this case, the two carbons are the same degree, so it doesn't matter which one you put it on. Either of these two particular examples could have been made by Williamson ether synthesis, but now they're just showing you how you could also do it with this mercuric acetate and this oxymercuration reaction. Now, aromatics, as I said earlier, do not do SN2 reactions because you can't invert this carbon, but you can still make aromatic ethers, as we saw an example earlier in the chapter. So if we wanted to make this ether, we could either do the Williamson ether synthesis, so we make this guy into the base nucleophile, and then do the SN2 reaction on this guy. Or we could do the mercuric acetate. Again, I have two different, two carbons here, but they're no difference in their degrees. Doesn't matter which one gets the carbon, which one gets the hydrogen, which one gets the oxygen. And so we can make this guy that. Probably people would make this by the Williamson ether synthesis if that was, what they were trying to do. But it does give us some options. But now let's start looking at molecules where it really matters. And, alright, so when we're looking at this molecule, we want to look at the degrees of the carbons that are directly attached to the oxygen. So this carbon right here is tertiary, and this carbon is secondary. And so, first thing that we realize is that both sides are a little bit crowded, and so maybe doing an SN2 in a Williamson ether synthesis would not be a good idea. So, so then we start thinking about, all right, so if we then want to try the alkene type reaction, then we have to look and see, all right, so that means one side would be an alcohol and the other side would be an alkene. And so we have to start thinking about, well, which side would be better to be which one. And remember that with the alkene, it has to go through, it's going to go through a Markovnikov process. So the oxygen group is going to get attached to the more substituted carbon, and the hydrogen would go to the less substituted carbon. So we need to draw some pictures. And so let's think about it this way first. If we were going to make this bond, then that means this whole piece over here would be the alcohol, and the double bond would have to be over here. Now it could be here or here would be the same difference, or it could be out here. If we put it out here, then this is the more substituted carbon, and the less substituted carbon is going to get the hydrogen, and the more substituted carbon is going to get the oxygen, and that is going to give us the right product. Our other choice then would be, what if we put the alkene inside the ring? So if we put it inside the ring, again, we think about the Markovnikov would put the hydrogen here and the oxygen group here, and that is the product that we want. So either one of these two alkenes would work in the oxymercuration process with this alcohol, would give us the right product. Now, one could ask the question, is that our only option? And so then we could look at it from the other side. Well, what if we let this side, all of this, be the alcohol, and let this side be the alkene? So that's what I've got pictured here. So you again use the mercuric acetate with this alcohol. Now, which one, do you choose? And you have these three different routes, basically, to get to the same molecule. in principle, they're all fine. And so, then you just have to decide based on perhaps, what you have available, or perhaps cost, or how easy is it to deal with this. Like, this is a gas. Maybe that's a little more trouble than dealing with either of these two molecules. And this alcohol is pretty common. This alcohol is maybe not so common. So, maybe I would choose one of the other of these routes over that, just for those reasons. But in principle, any of these would work. All right, so let's try this again. All right, so we want to know, how can we get to this ether? So we're going to look at this carbon that's attached to the oxygen, and this one's a secondary, and this one is primary. So when you ask yourself the question, if I wanted to make this alcohol, could I do a Williamson ether synthesis? Since this carbon right here is primary, then maybe I could do a Williamson and let the substrate be this side, and this side be the alcohol anion. So that's the first thing to ask, and so, yeah, maybe so. It's going to require a little bit of a bulky nucleophile, and but in principle, you could see how that looks. This is how it would look. You'd have this alcohol, make that into the anion, and then this be the substrate, and do your SN2 on that. It's a little crowded, and so if you were in the business of making this molecule, you might try that to see, how it goes. And, you would probably get some of this, but maybe you're not satisfied that you're not getting very good yields, so you might want to consider what else you could do. And so then we want to look at it to see if the oxymercuration would work. And so, again, now we have to think, all right, so one side would be an alcohol, the other side would be an alkene. Now this time we have to be a little bit careful in how we pick this. Because if we put the double bond here, then the oxygen would go to the more substituted carbon, and that would work. But what if we put the double bond here? You see, what would happen is that the oxygen would end up on the more substituted carbon. So we can't use just any alkene from this side. If we put the double bond here, then it would be all right, because it wouldn't matter which one it's going to, it wouldn't matter which one of these we let have the double bond, but we wouldn't get the right orientation. So you have to think about Marconica. So if we had the double bond here, and we put in our alcohol, you see it would attach to the more substituted carbon. But that's not what we want. So if we put the double bond here, so we see the different degrees, which carbon is the more substituted? This one. And so it would give us, again, not what we're trying to get. We don't want that either. So we're going to have to put the double bond here, and then we can get that to work. And that one's okay. So the bottom line is, in looking at this ether, we have a Williamson route, which is pretty reasonable, and an oxymercuration route, which is also reasonable. And we have things that would not work. So these are the things you have to take into consideration when you decide what's the best way to make an ether. And it was all predicated on first looking at the degrees of the carbon that are attached to the oxygen. And I'm going to stop this recording now.